Hi, today we are diving into the critical issue of cyberbullying and how we can leverage advanced machine learning techniques to detect and potentially prevent it. Our objective has been clear to develop a robust neural network that can accurately identify cyberbullying from social media text. We utilized the comprehensive cyberbullying tweets dataset available on Kaggle. This dataset includes diverse examples of cyberbullying categorized by type, such as gender based or ethnicity based, which provides a rich basis for training our model. In our approach, we explored three main architectures: a GRU based model for its efficiency in sequence processing, a CNN based model for robust feature extraction, and a BERT based model to leverage state of the art language understanding. The pre-processing steps were crucial. We cleaned the text data, removing any web links, user mentions, and non-relevant characters. Following this, we used tokenization and glove embeddings to convert text into a format suitable for deep learning. Our models were trained using the Adam optimizer with categorical cross entropy as the loss function. Techniques like dropout and batch normalization were employed to combat overfitting and improve model generalizability. Model performance was meticulously monitored through accuracy, precision, recall, and the F1 score. These metrics helped us understand not just how often the model was right, but how it was right, providing insights into the predictive capabilities. We visually analyzed the training process, charting accuracy, loss, and other metrics over time. These plots not only demonstrated the learning curves, but also helped pinpoint when the models were underfitting and overfitting. Now let's dive into the coding part. We begin by installing key Python libraries that will power our data handling and model training processes. This includes libraries for video and audio processing, speech recognition, and neural network construction. This step involves loading essential libraries and modules needed throughout our project. Here we load the cyberbullying tweets dataset, which provides us with raw text data categorized by types of cyberbullying. In this crucial step, we pre-process the text data to clean and normalize it, making it suitable for machine learning models. This involves removing text elements like URLs and user mentions, lowering all text to create uniformity, and reducing words to their base or root form through stemming. To understand the scope of cyberbullying types we are dealing with, we extract unique labels from our dataset. This helps us identify the range of cyberbullying categories, facilitating the setup of our model's output layer to classify these types accurately. Given the variety of cyberbullying forms, we simplify our model task by consolidating specific categories into single cyberbullying label. This code is about transforming the cyberbullying type column into a format suitable for training our neural networks. We use label binarization to convert category labels into a binary matrix representation. We then tokenize our text data, converting strings into list of tokens or words that our model can understand. After setting up our tokenizer, we finalize the preparation of our model inputs by repeating the tokenization for any new or remaining text data and ensuring all input data is appropriately padded. Knowing the exact number of unique classes or categories in our dataset is crucial for setting up the output layer of our neural network correctly. We utilize glove pre-trained word vectors to create an embedding matrix that will transform our tokenized text data into dense vectors of fixed size. To rigorously evaluate our model, we implement a custom F1 score metric which combines precision and recall into a single measure. This is particularly useful for balancing the trade-off between precision and recall. We define our neural network architecture using sequential layers in Keras. This includes an embedding layer loaded with pre-trained vectors for depth, GRU layers for sequence processing, and dense layers for classification tailored to predict the type of cyberbullying. Next, we compile our model, setting up the optimizer, loss function, and metrics, and then train it using our pre-processed data. We also employ callbacks like early stopping and reduce plateau to optimize training, avoiding overfitting, and adjusting the learning rate dynamically. Post training, we visualize the model's training process through various plots displaying accuracy, loss, precision, and F1 score. This visual assessment helps us understand the model's learning behavior over epochs, allowing us to verify its effectiveness empirically. This code segment demonstrates the model's ability to make predictions on new processed data. Here we process a sample text, convert it into a sequence, tag these sequences, and then feed them into a trained model to predict the category of cyberbullying. Let me just run the code. Here we can see that the model has predicted other cyberbullying for the pre-processed text. We extend in this code we extend our model's application to audio inputs by converting speech into text using the speech recognition library. This code illustrates how to pre-process audio files, convert them into a suitable format for text analysis, and use our trained model to predict the nature of the content, demonstrating the model's versatility across different media types. In this code, we define an alternative neural network architecture using convolutional layers. This model is particularly good at capturing spatial hierarchies at data. We include a spatial dropout and batch normalization to optimize training and prevent overfitting. Here we compile and train the convolutional neural network model employing callbacks like learning rate reduction on plateau to enhance model performance. We visualize the performance of the CNN model through the same metrics that we have used for the previous model. This code allows us to apply the CNN model to new text data, demonstrating its use in real-time applications. Here we can see that the model has been correctly predicted the class using the original text. We show the model's capability to handle spoken input by converting speech to text and then predicting its category using our trained CNN model. Now we are using a pre-trained transformer model, BERT. We set up a sophisticated architecture tailored for sequence classification. This setup involves preparing datasets, defining the model, and specifying training procedures, highlighting the advanced capabilities of transfer learning in tackling complex classification tasks. In preparation for training the model, we encode labels, split the dataset, and create data loaders. This structured approach ensures that our data is optimally organized for efficient training, leveraging the robustness of the BERT architecture. This segment involves the actual training of the BERT model, where we implement a training loop that optimizes the model across several epochs, adjusting learning rates dynamically. Once training is completed, we save the model and tokenizer configuration. We graphically represent the training results of the BERT model, comparing training and validation metrics. This code demonstrates the application of trained BERT model to new textual data, predicting cyberbullying categories. Here we apply our BERT model to audio data by converting speech to text and then to predictions. In conclusion, our project demonstrates the effective application of advanced neural network models, including GRU and CNN architectures, as well as the cutting edge BERT model to the pressing issue of cyberbullying detection across various media types. By leveraging natural language processing techniques and deep learning, we have developed a system that not only identifies cyberbullying with high accuracy but also adapts to different formats of input such as text and audio. Thank you.